So we have now, just to review, what I would recommend doing is like on the back of your packet or on a separate sheet of paper, keeping that as kind of a reference sheet. So every time I give you a new equation, I'm like, oh, this is an important equation. Then put it down somewhere. Okay. But there's another equation I want to give you right now. And I hate to just give you equations and tell you this is how it works. So I want to go through the derivation for it and explain where it comes from. Notice all of our equations, the position, the velocity, even the definitions of velocity and acceleration, they all have time in them. But there might be a situation where you're solving a problem and you don't have the time. They didn't give you the time. And so there's an equation that doesn't have time in it. But again, I don't want to just give it to you. So here's where it comes from. We start with the position function, but I'm going to solve it for displacement. So delta x equals v naught t. Actually, I'm going to call it vi because I'm going to get vi and vf in this equation. Delta x equals vit plus 1/2 at squared. All right, now what I'm going to do right now is I'm going to solve for a, and you'll see why. Later you'll see why. Okay, so delta x minus vit equals 1/2 at squared. Now if I want to solve for a, I'm going to multiply both sides by 2 over t squared. I'm doing that for these things to cancel out. So I'm going to multiply this side by 2 over t squared. What I get now is 2 delta x over t squared minus, now the t here, so I get 2 vi, and the t on the top cancels out with one of the t's on the bottom, so this ends up being 2 vi over t equals a. All right, I solved for a like I wanted to. The thing is, I have another equation for a. A equals delta v over t. So I'm going to substitute this now in here for this. Okay, so 2 delta x over t squared minus 2 vi over t equals delta v over t. All right, this is nice because if I multiply both sides by t, some of the t's cancel out. Right? This cancels out, and one of these t's cancels out. Okay. Next step in the equation. I've got 2 delta x over t equals, minus 2 vi, now there's no t there, equals delta v. I'm going to write out what delta v is. Delta v is vf minus vi. Okay. Now, my next step. I'm going to add 2 vi to both sides. So that gets rid of this. And my new equation will look like this. 2 delta x over t equals vf plus vi. Okay. Now I haven't succeeded in getting rid of time yet, have I? Right. Okay. But here's what I'm going to do. I have this t hanging out down here, but if I multiply both sides by delta v, then I can put the t into acceleration. Let me show you what I mean. So multiply both sides, multiply the whole thing by delta v. So now I end up with 2 delta x times delta v over t. It seems like I just made that more complicated, but you'll see what happens in a second. Vf plus vi times Vf minus Vi. All right. Now this is acceleration. So now I have 2, I'm going to write a delta x. I just switch the order, equals. This might be a little boring. I apologize. But I want to assure you that it's interesting. So this ends up being a difference of 2 squared, right? Vf plus Vi times Vf minus Vi. Remember that from algebra? Vf squared minus Vi squared. Okay. And so this is it. Now I have an equation that doesn't have time in it. If I know the initial velocity, the final velocity, if I know the acceleration, the displacement, or any combination of those things, I can solve for the others using this equation, and I don't need to know the initial velocity. I don't need to know the time. Okay. I'm going to write this a different way. This is how it's normally written. Vf squared equals Vi squared plus 2a delta x. What I just went through is what we call a derivation. Okay? We derived the no time equation. I sometimes call this just the Vf squared equation. Right? That's where it comes from. So now you don't have to just trust me. You've seen it for yourself. And if you need to, you can go back and reason through it. Right? But this is another one that you want to write down somewhere on a reference sheet. Keep track of it, because it does come in handy sometimes. By the way, before we move on, I want to revisit this. So you see this derivation, what happened here? I took a couple of equations, and then things got really messy, but then I was able to put them together again and resolve them in a kind of succinct, usable form. Right? This is part of what the physicists talk about when they talk about the beauty of physics. Okay? That you can just kind of perform these manipulations mathematically. You get a simple formula, but then this formula actually works. It actually describes reality. Like, what was I doing? It just felt like I was doing algebra. You just feel like you're in math class, kind of crazy math class, where you've taken most of the numbers out, and we've got some exponents, but then that's it. It's just all these letters. Right? But the letters mean something, and then when we combine them, distribute them, recombine them, substitute, we end up with this formula that works. It actually works for describing reality. And that's a mind-blowing thing that the physicists call beautiful.